As we've already mentioned, there's a clear correlation between venous return and cardiac output and a normal functioning heart. So venous return, as we've already said, is mean systemic filling pressure minus our right atrial pressure over our resistance to venous return. And we can represent all of this on a graph and discuss it further if you draw on your y-axis venous return or cardiac output in liters per minute. And remember, like we said, venous return should be the same as cardiac output. But we can demonstrate when things go wrong on this graph as well. And then on the bottom, on our x-axis, we'll draw right atrial pressure, and this is in millimeters of mercury. So ideally, when you draw this graph, it helps if you start at -2 and you go all the way higher than +7. So I'll just add on +7 here, and we'll move it up to about 9 millimeters of mercury. The first line I like to draw on this is in red, our cardiac function curve. So generally when you do this, you'll start at -2 and you'll have the plateau happen at about 4 millimeters of mercury. So the reason why we start at -2 at the x-intercept is just purely because it's extrapolated from data that as cardiac output dropped. This is what they just assumed it would be in the original Guyton papers and the way it was originally drawn. The plateau that you can see essentially represents the ceiling of the cardiac function. As we know, cardiac function isn't infinite. Eventually you'll reach a ceiling where you can't go above this, such as, for example, with the Frank-Starling law of the heart when it comes to preload, but you also see this with things such as afterload. I've linked a video where I explain the left ventricular pressure volume loops, which help us understand these ceiling effects just above as well. The next curve to draw is the vascular function curve, and I'll draw this in blue, but before I do, I just want to mark the 0 line going up from right atrial pressure. Now, this is important because at this point, your vascular function curve, once it hits 0, it has to flatten out, because once you go less than 0 and you head into negative numbers, you get collapse of the vessels. So they'll collapse inwards and block themselves off, which will block off any further venous return here. The other important thing to note is where the vascular function curve crosses the x-axis is the mean systemic filling pressure. So I know that it says right atrial pressure along the x-axis, but the right atrial pressure is represented by the steady state point of the intersection between the vascular function curve and the cardiac function curve. At this point, this is the right atrial pressure, but where the blue line crosses the x-axis, that's the mean systemic filling pressure. And the mean systemic filling pressure will always be greater than the right atrial pressure because, as we know, you need to go from a higher pressure system to a lower pressure system. So your mean vascular function curve should always have a mean systemic filling pressure that's slightly greater than the right atrial pressure. And I'll demonstrate this further later in the video. But you can see here at the steady state point, the steady state operating point, it'll be at the level where venous return and cardiac output match each other, which demonstrates the intimate relationship we've already described between venous return and cardiac output. This graph is quite interesting in that it allows us to also apply different scenarios and see what our cardiac output and venous return would be like, and also estimate our right atrial pressures and sometimes our mean systemic filling pressures as well.